Right, so the 2010 one, right? So let me put the structure on the board. So we're starting with alkenes, right? But tell me, what is the characteristic reaction of alkenes? If I use the term characteristic, what do I mean? What type of reactions alkenes do compared to alkenes?
You mean like the electrophilic addition?
Alright, addition. Right. Alkenes always do addition and alkenes do substitution. Why alkenes do addition? Joanna, why can alkenes do addition whereas alkanes only do substitution?
So because alkenes, because it's double bond, they can break and form another bond, but with
Right,
alkenes, it's full, it's saturated, it can't.
right, correct. Force in the bonds, right? Just a second. Tell me, send which one of the link? There?
Yeah.
Alright. Right, so we have our alkene here. So the first question now, alright, let me just put it out. So Br2, if we react the alkene with Br2 liquid, so remember it can be aqueous or it can be liquid. So in the question, we are using liquid bromine. So what will happen when we add liquid bromine to this alkene? And let me put the carbon of the double bond in blue. So whenever the alkene is reacting, whenever the alkene is reacting, right, we know that the reaction takes place at the carbon to carbon double bond. So if you're adding bromine, both of them should go to each carbon of the double bond. Right? Everything else in the structure will stay the same. All we're doing, hold on, all we're doing is breaking the double bond and add two atoms of bromine. So everything else will stay the same. So we will still have the CH3 group, right? And over here, we will still have our hydrogen and the CH3 group. So whether it's alcohol, alkenes, any organic compound, the reaction is always taking place at the functional group. That means the rest of the structure will remain the same. So this is it if we add liquid bromine to it. So that would be the structure for compound C. So this is compound C. For compound B, we are reacting it with cold potassium permanganate. So if we react it with cold potassium permanganate, what do we expect to form? Camille, what do we expect to get if we react it with cold?
A diol, each carbon atom going to get a OH group.
That is correct. So each carbon atom of the double bond will get an OH group. And it's supposed to be acidified, right? Which acid do we use to acidify it? Which acid? Benjamin.
Nitrous acid.
Repeat. Which acid we use? Benjamin. Camille, which acid we use?
Is it sulfuric acid?
Right. So the slash H plus, and if you see a slash H plus, it means it is acidified. So Br2 liquid, it has two Br atoms. If it's cold potassium permanganate, they get the diol. So the general name for it is a diol. So each carbon atom gets an OH group. Alright, so now for the others now, it says state the reagent and conditions necessary for each of the reactions. So from A to B. Can you tell me the name of the reaction occurring when it is converted from A to B? So we put B on the board.
Sir, is it oxidation?
Right. And how do we oxidize it? What is the oxidizing reagent?
Hot KMnO4.
Right. Hot KMnO4. Still acidified. Right? And remember, without even looking at the structure, right, that is on the paper, what should happen? So without looking at the structures given on the paper, when we use hot potassium permanganate, what happens to the double bond?
Sir, it is cleaved.
Right. So if we cleave the double bond, what happens next? So, let me put each carbon of the double bond, right? Because it is now broken. What happens to each of them?
Each carbon have a double bonded oxygen.
Right. And then all you have to do is put back everything that was there. So when it's hot potassium permanganate, the double bond is going to be cleaved, and each carbon is converted to the carbonyl group. Alright, so C double bond O, this carbon, it had methyl groups attached to it, so we put them back on. Alright, so CH3, CH3. What is this compound? Which functional group is this?
Ketone.
Ketone, correct. What is the name of it? The IUPAC name? What they call?
Unknown.
Right. And for this one, we have the hydrogen, and we have the CH3 group. Alright, so which functional group is this one? This is a ketone.
Aldehyde, sir.
Right, aldehyde. Now, if it's an aldehyde, what do we know about what will happen to the aldehyde?
We will easily oxidate acid.
That is correct. So, we will get the aldehyde, but it will be converted to the carboxylic acid. So, our final product, it will not be the aldehyde. The aldehyde will be further oxidized to a carboxylic acid. Right? And which carboxylic acid is this?
Ethanoic acid.
Right. Right. So, for this part of the question, all it needed was to give the reagent. So once you see you have the alkene, and you see you get two products, so we know that the double bond was cleaved, and they gave us the ketone and the acid. So we know we use hot potassium permanganate. Alright, so the other one left now is alcohol. So what is the name of the reaction in which we get an alcohol from an alkene?
Hydration.
Yes, hydration. Alright, what is the reagent for hydration? What do we add to the alkene to get the alcohol? What do we add to the alkene? It is hydration. What
Sir,
are
what?
we exactly
Water.
right? Right? It, uh, yeah. Um, three, three. So all we're doing is adding um, water here. So this hydrogen is from the water. So OH goes to one carbon atom and the H goes to the next one. Now, just like with the addition of HBr, we are going to do this same thing with the water. So in this compound, this carbon, right? Let's look at it from this point. This carbon atom has one hydrogen attached to it, right? And this carbon atom has two methyl groups. It does not have any hydrogen. So following with Mark chemical rule, you put the hydrogen and the carbon that already has more hydrogen attached to it, right? Or you can look at it from a next perspective. Which of these carbocation would be more stable? And so this carbon, right, it has two methyl groups attached to it, right? And this carbon has one methyl group attached to it. So which one would be more stable? The one with two carbons or the one with a single one? Which one would be
The
more
one
stable?
with two carbons.
Right. Hence, this goes here. So you can look at it in terms of the carbocation or in terms of the hydrogens. So the OH goes to the carbon with less hydrogen, or it goes to the more stable carbocation. Right? So the reagent here, okay, so the reagent, just like it above, we use water, right? But what is the catalyst for this reaction? Other than water, we also add what to it,
Sulfuric acid.
right? Sulfuric acid, right? And heat. Right, so those are the reagent are the water and sulfuric acid, and the condition we apply heat. The sulfuric acid is the catalyst. So this is A2. I can just read it on the board. This is E. Right, so this is A2. So this was A2, water, sulfuric acid, and heat. And this was A1. Potassium permanganate. We already drew the structure for B and C at the start of the question. So this one was,
Sir, at 2010.
yeah, 2010 first.
Oh, okay.
Yeah,
The one with the cool, hot, and all of that.
right. Yeah. So we did A, B, A and B. There's an next part to it. Was there an next part to them? Yeah, right. So this was one of the 2010. So the next 2010 now, let's move to the next one. That says question 4. So we're going to do question 4 now of 2010. So let's skip across to number 4 of 2010.
Excuse me, sir.
Yeah,
Did we draw the structures of B and C? That was asked for number one.
yeah, that was the first we did. Alright, let me show you about. Just a So all you would do, right, for B, just a second. B is when you add, so the double bond will break, right? Because we're using cold potassium permanganate, so you will get the formation of a diol, right? So each of the carbon atoms of the double bond would get an OH group. So that's the structure of B. Right? And of course, you would put on back everything that was here. And for C, we add liquid bromine to it. So again, you break the double bond, and because it's liquid bromine, we're going to add a bromine atom to each of the carbons. If it was aqueous bromine, what would have been the difference?
We're going to have Br and a OH.
Right. All right, so let's move to number 4 now. You can try to answer it in the meantime. All right, so we are given 2 isomers, and it says 2 structural isomers, A and B. And it says explain why A and B are structural isomers. So from it says A and B are structural isomers, what does that mean? What would have to happen for them to be structural isomers?
They have the same formula, but different arrangement.
Well, what kind of formula? The same what?
Same molecular formula.
Right? But different.
Structural formula.
Right. So name 2 functional groups present in both molecules. Jonah, give me one.
Wait, sir, repeat the question.
So we're doing question number 4, the 2010 paper. Are you there?
Yes, sir.
Right. So for part B now, it says name 2 functional group present in both molecules. So which functional group is present in both?
Alkenes.
Right. So both of them. So number 4B, both of them have the carbon to carbon double bond.
Sir,
Yeah. Go ahead, John.
no, I thought I was supposed to answer both.
No, always wanted one. Record, give me the next one.
Sir, can repeat?
Alpha.
There's a,
Not hearing.
oh, so we're doing part B of number 4,
Okay.
right? Go ahead, Ricona.
We're saying if alcohol is one, the OH.
So the carbon to carbon double bond is present in both groups, and the OH is present in both of them. And for some reason, when we ask for functional groups, students ignore the carbon to carbon single bond, but remember, it is still a functional group for alkenes. So the carbon to carbon single bond, that is a functional group as well. So that's part B. So for part C now, it says A and B also show stereo isomerism. Draw the discrete formula of A and insert a parallel carbon. I want you to try this one. So draw the discrete formula of A and B and identify the chiral carbon. So I'm going to do that on the board as well, but you can do it in the meantime. So this is compound A. Right, yes, so it asks for us to identify chiral center in compound A. So starting from this end, so remember, how do we identify a chiral carbon? So who is here?
The carbon with 4 different groups attached.
Right. And remember, we are going to identify the group, so you have the carbon atom, right? Whatever is attached at the top, that's one group. Whatever is to the left, that's the next group. Whatever is to the right, below, that's the next group, and to the right, is the next group. Not just the atom directly attached to it. Anything to the right is a group, anything to the left, anything below, anything above. So if we look at this carbon atom, the first one, is it a chiral carbon atom? Not enough. Is this carbon atom a chiral carbon? Does it have 4 different groups attached to it? Ashante?
No, sir.
Alright, good.
No, sir.
Alright, we see 2 hydrogen attached to it. So let's move to the second carbon. Continuing with Shante. Is it a chiral carbon?
No, sir. There are 2 hydrogens attached.
Right. Continuing to this one. Can this one be a chiral carbon?
Yes, sir.
Tell me why. Tell me the 4 groups.
Because the methyl group,
Right, so this is one group.
yes,
Tell me the next
the
group.
full group on your right,
Right, this,
the
the third.
hydrogen,
And so that's the next group, the hydrogen. That's
and
3.
then the one on your left hand.
Right, the ethyl group. Right. So that's a chiral carbon. Good. Do we have any more? So let's check. Would this one qualify?
No, sir, 2 hydrogens.
Right. Would this has 2 hydrogen? This carbon, how many groups does it have attached to it? Does it have 4 groups? Does it have 4 groups attached to it? This carbon,
No.
right? So any carbon with a double bond, it cannot be chiral because it must have 4 groups around it. And once it has a double bond, it is not going to, it will not form 4 bonds. For carbon to form 4 bonds, it has to be 4 single bonds. So none of these carbons can be chiral. Alright, and then this one clearly 3 hydrogens attached, so it cannot be chiral. So the third carbon from the left, that's our chiral carbon. Then it says draw geometric isomers of B. Alright, so let me erase A. Everybody over here. So what's the next name for geometric isomers? Geometric isomers are also carbon.
Sisters.
Correct. And so B now, so remember to identify your geometric isomer. Alright, let me draw the structural formula first. Alright, so CH3. CH3. And so there we have it. So remember now, when you want to do geometric isomers, and so let's put on the H on this. you locate the carbon to carbon double bond in your compound. Alright, so this is it. So let's find the carbon to carbon double bond. Then we'll set it up in the cis-trans configuration. First of all, does it have cis-trans isomerism? What is one of the main criteria?
So it has both a element must be in common with each carbon atom.
Right, or a group. So each carbon atom of the double bond of an atom or a group in common. So in this case, both of them have a hydrogen atom. So that means if we put the hydrogen atom on the same side, we are getting, which configuration is this?
Cis.
Right. And then now, CH2, CH2, CH2. Then just draw out everything afterwards. CH3. And then this side of CH2OH. So that would be the cis. And so for the trans, you just flip any side of the molecule. So let's do that. You could have done the condensed formula if you wanted as well. Right? So you don't have to draw the structure. As in, you would do it for here, but then you could just write CH2, 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 and continue. Right, so that is it. So this is trans, and this one is cis. Right. So remember, cis trans, locate the carbon atoms of the double bond and just set it in the cis trans configuration. And just place back everything as it was in the compound. So all of it, locate the carbon atoms of the double bond. Alright, and I set it in the cis trans configuration. So the two hydrogen goes up top, that is cis. Attached to this carbon is the hydrogen, everything else it comes down here. CH2 and I just follow it. Same thing for this carbon, it has the hydrogen and then CH2OH. Down here, just put the hydrogens across from each other. This one, I chose to put this one. I could have done it with this one. So I carry this up and bring the hydrogen down. So whichever one you prefer, it's okay. Alright, so that's cis and trans. The next
So, sir, why doesn't it have isomers?
is a bit.
So the question says,
Yeah, man,
suggest why B has no optical isomers.
right, so you have to tell me that now. What is an optical isomer? How do you identify an optical isomer?
Sir, B does not have any chiral center.
Right. So remember, alright, how do we identify the chiral center, Rikona?
Like I said, 4 different compounds is attached to the carbon.
Exactly. So that means there are no carbon atoms with 4 different groups attached. And if we start from here, this carbon has 3 hydrogen, so it cannot work. This carbon has a hydrogen, a CH3 group, but remember, this is also a CH3 group. So let me just do the condensed formula so you don't think it's a different group. It is still CH3. Alright? So this carbon, it has 2 methyl groups attached to it. Alright, so it's not chiral. We move to this carbon, it has 2 hydrogens. Alright, this, we cancel that, right? These 2 carbons only have 3 groups attached. This carbon, 1 group, everything on this side, that's a group, and this is a group. So that's 3 groups, and it must have 4 groups. This carbon here, it has 2 hydrogens, so it cannot be chiral. So there are no chiral centers, no chiral carbon present in the compound. So it cannot be an optical isomer. Alright, what is meant by the term cracking? Anybody? Which homologous series undergoes cracking?
Sorry, it's where one hydrocarbon is broken up into small hydrocarbons.
What kind of hydrocarbon? Because remember, you have the alkenes and the alkanes. So can both of them undergo cracking?
So is it the alkane alone?
Right.
So isn't it? Oh, never mind.
So alkanes, so cracking is the breakdown of large saturated hydrocarbons. And we know the saturated hydrocarbons are alkanes, right? Into smaller saturated hydrocarbons as well as what? So when you crack an alkane, you must always get 2 homologous series. Smaller alkanes and what else?
An alkene.
Alkene.
Right, alkene. So we crack alkane, and when you crack the alkane, you must get smaller alkanes as well as an alkene. At least one alkene. So any compound you crack, any alkane, you must get a smaller alkane and alkene. So in this case, they give us octane, and it says it undergoes cracking to produce 2 hydrocarbon fragments. They could have said 3, right? But in this case, they tell us that octane undergoes cracking to produce 2 hydrocarbon fragments, each containing the same number of carbon atoms. Write the equation to represent the process above. And so octane is CaH18. And they said it undergoes cracking to give 2 hydrocarbon fragments containing the same number of carbon atoms. So if you have 8 carbon atoms, how much carbon must be in each fragment?
4.
Right. So C4. Now one must be an alkane and one must be an alkene. If this one is the alkane, how much hydrogens should it have?
10.
Right.
10.
Right. And if this is the alkene, it should have
8.
8.
right. Remind me of the general formula for alkene and alkene.
Alkane is 2n plus 2 and alkene is 2n.
But don't leave off the
And the
n part. So CnH 2n plus 2 and the alkene is CnH 2n. Right. So this much is the alkane and this much is the alkene. What is the name of this alkene?
butane.
Butane.
Sir,
Please repeat.
should something be on the arrow?
Speak.
No.
Right. Alright. What would be the name of this alkene?
Butane.
Alright, so we get butane and we get butene. So for part B, sorry, describe a simple laboratory test to distinguish between these two hydrocarbons. So describe a simple laboratory test. So what can we use to distinguish between an alkene and an alkane?
Sir, could we use bromine water?
Right. Or bromine water on the next one.
Can you use the potassium permanganate?
Right. So describe a simple laboratory test. Alright, so the addition of bromine water. Right. So once you see aqueous bromine, it's bromine water, right? So the addition of bromine water to alkenes and alkanes can differentiate between the two. So all we would need to do is what? Pour a small amount of each compound into two test tubes and add a few drops, not a few drops, buttermilk. I can put
Sorry, I
a,
made a mistake.
which part, tell me?
In two test tubes, you have in two separates.
As a first into two separate tons. Alright, so I will do pour a small amount of the butane in one test tube and the butane in the next one, and add a small amount of the bromine water. Now, what would we expect to happen?
Sir, the butane will decolorize the bromine water.
Right,
Well, the butane will decolorize it, but only in the presence of UV light.
that is correct. And that's 15 marks for you. Alright, so that ends the 2010 paper. And so let's look at the O9 question on stereoisomerism. When you're ready, you'll let me know.
Yes, sir.
Alright. Alright, so stereoisomerism. How would you define stereoisomerism? Anybody?
So it's when a, a molecule or a compound is connected has the same arrangement, but the atoms are connected differently.
Repeat that for me.
It's it's when the compound has the same arrangement in terms of they have the same atom, but they're connected differently.
No, the connectivity is the same, but the arrangement in space is different. And so it's stereoisomerism. The atoms, so this is a form of isomerism in which two or more molecules, right, of the same molecular formula. The atoms are bonded in the same way, right? But they differ in their arrangement in space. So it's a form of isomerism. So a form of isomerism in which two molecules have the same connectivity, that is, the atoms are bonded the same way, but differ in their arrangement in space. So just remember, the atoms are connected the same way, but they differ in their arrangement in space. And then they ask for a chiral center. You know, a chiral center, alright. If I ask you to identify a chiral center in this compound, what would you be looking for?
The carbon with 4 different groups attached to it.
Alright, so how would you define chiral center? Because I just did. So define it to Rickon. What is a chiral center?
Any carbon with 4 different compounds attached to it?
With four, don't use compound, use groups.
Yes, sir.
Yeah. And it don't have to be carbon. Right? So it can be carbon or any atom with four different groups attached. So that's good.
So what can it be? It doesn't have to be carbon.
No. So any atom at all with four different groups attached. But in most cases, it's carbon, especially it's organic chemistry. So, and this compound, which carbon is the chiral center?
Carbon 2.
Right. This one in the middle, right? And what is the name of this type of isomerism? So that is our,
Would it be optical isomerism?
that is correct. So once it has a chiral center, we refer to them as optical isomers. So this carbon is the chiral center because it has four different groups attached. Right? So this is right the displaced formula of the two isomers. So this would be one isomer. Right. Let me erase it and write again so I can have enough space. But what would be the next isomer of this compound? How would you get the next isomer for it? If it's optical, what would be the isomer for it? How do we get optical isomers? Optical isomers are what of each other? Jonah? Long time.
Is it that they are mirror images?
That is correct. So all you need to do to get the next isomer is to do what?
You switch this.
Right,
Like the
just flip.
carbon part, you go over where the end part is. The end
Right,
part.
exactly. Because if it's a mirror image, you basically flip over the molecule. So the chiral carbon in the center, the NH2 group,
Sure, I know the carboxylic group supposed to be reduced.
Sir, no.
yeah. C double bond O, OH, and this to the back. Two. Right. So if you should take up this molecule, before I say it, optical isomers, they are said to be what? What type of mirror image? Optical isomers are dots.
Non-superimposable.
Correct. The optical isomers are non-superimposable mirror image of each other. And what does that mean if you say they are non-superimposable?
If you take up the
Sir,
compound where it not fit on the other one,
Right. So if we should take up this, right, and just place it on this, the NH2 group would align with the carboxyl group, and the carboxyl group will align with the NH2 group. So they are mirror images of each other, but they are non-superimposable. Alright, wonderful. And that would be 6 marks for you. Alright, so yeah, that's it for the 2009 paper. So let's move to 2018. Alright, so for number 1, alright, well, so figure 1 shows the reaction sequence of an organic compound A producing compounds B and C. Alright, so compound A has a methyl group, CH. Alright, so there you have it. I know to put a double one here because based on the condensed form, right, it says CH3, CH, then it says C, CH3. Now, if I follow the condensed formula, this carbon would be short of a bond, right? Because each carbon must have 4 bonds. And we see that this carbon would be also short of a bond as well. So if 2 of them are short of a bond, it means that the double bond must be here. It couldn't be here because this carbon has 1, 2, 3, 4 bonds. And this carbon has 1, 2, 3, 4 bonds. So the double bond must be between these 2 carbon atoms. So we have ourselves an alkene. What would be the name of this alkene? Anybody? Jonah? What
Can
is
you
the
repeat
name,
the question?
what is the name of the alkene of compound A? This is compound A. What is the name of it?
Sir, is it 3-methyl pentene?
Where is, tell me where the double one is. So don't just say pentene.
Sir, repeat. Oh,
Don't,
I heard it one. There would be on the second one.
alright, so repeat the name now.
3-methyl
Mm-hmm.
pentene.
Alright, so 3-methyl pentene. If you want, you can say 3-methyl 2-pentene. Alright, so that is compound A. So if we write compound A with HBr, what should we get?
haloalkane.
Right. Alright. So all we're doing is adding HBr to the carbons of the double bond. Alright, so CH3, adding of CH3 and hydrogen there, right? Also of CH3, CH2, CH3. So the question is, where do we put the hydrogen? Which carbon do we put the hydrogen on? And which one do we put the bromine atom on? Alright,
The hydrogen and
what about this carbon?
second carbon, and the bromine on the third one.
Alright, and why do we do it? Who said it? What is the name of this scientist that said it? Start with an M.
The mark of this thing
Mark,
pregnancies.
right, Markovnikov's rule, right? So in the addition of a hydrogen halide to an alkene, the hydrogen of the hydrogen halide goes to the carbon of the double bond bearing the more hydrogen. So clearly, this carbon of the double bond has more hydrogen than this carbon. So that is where we put the hydrogen. Right? So this would be compound. That is structure of compound B and C. So this is the structure of compound B. What is the name of compound B? Dubidot. What's the name of compound B?
Sir, let me check. 1, 2, 3, 4.
Take your time, take your time.
So 3 bromo,
Alright.
3 methyl
3
pentane.
methyl. Pentane. So 1, 2, 3, 4, 5 carbons. Doesn't matter which direction we come from, the methyl group and the bromo group will be on carbon 3. So counting from this end, 1, 2, 3. Counting from this end, 1, 2, 3. So it doesn't matter which direction, it will be 3 bromo, 3 methyl pentane. Alright, good job. So now the next one, so this is compound B, and now we're converting compound B to compound C. So, who can tell me the product? What would be the product of C, as in the name of it? Or tell me the functional group that would be formed. What will you get? Which homogeneous series? Alkene, alkene, alcohol, carboxylic acid. Which functional group? Which homogeneous series, sorry. So remember, this is a haloalkane, and we are reacting the haloalkane with sodium hydroxide. So if I make here haloalkane and sodium hydroxide,
And alcohol?
that is correct. And what is the name of this reaction, Nicola?
Is it dehydration?
But haloalkane,
The mechanism thing?
yeah, what is the name of it?
For the
Nucleophilic
nucleophilic,
substitution.
Right? But we have two types, right? So based on the structure, can you tell me, all right, tell me the two types of nucleophilic substitution.
SN1 and SN2.
All right. So which one will it do, SN1 or SN2?
SN1
Tell me why you say SN1.
because it's a tertiary carbocation.
Right? And how you know that?
Because the carbon that's attached to the bromine has 3 other carbons attached to it.
That is correct. So, let me just erase this. So if you want to know what type of haloalkane you have, and therefore what kind of carbocation will be formed, you highlight the carbon to halogen bond, right? So this is the carbon with the halogen on it, and directly attached to it is 1, 2, 3 carbon atoms. It's three carbon atoms, it is tertiary, as we could have pointed out, and so it will do SN1. And what will happen, as in for the final product, where will the OH group, which carbon atom will the OH group go on? Will the OH group go on this carbon? It will go on which one?
The third one, it would replace
Right, the one with the bromine. Mhm. 5 carbons, OH, right? And so we have our alcohol. The ethanol is this solvent, right? So sodium hydroxide, you react it with the L-alkane, you will get the alcohol. Nucleophilic substitution, because the hydroxide ion of the sodium hydroxide replaces the Br. So that is the structure of compound C. Anil, what is the name of compound C?
So 3-methyl pentanol,
Where is the OH group?
3-methyl 3-pentanol.
Alright. Or we can say 3-methyl pentan 3 alk. Right. So that's structure B and that's structure C. Right. So it says identify the reaction mechanism leading to compound P. So when we go from alkane to the addition of HBr, what is the name of the mechanism?
Electrophilic addition.
That is correct. And then, right, we already said nucleophilic substitution. And you would specify it, you can put SN1 in bracket. Give me a second, I'm going to plug in the laptop. It might freeze for a second, for a couple seconds. All right, good. Right, so this is electrophilic addition. This is nucleophilic substitution, specifically SN1, because it is tertiary. This is electrophilic addition. Let me just write it out. So this is the mechanism when you add HBr. And this is the mechanism for haloalkanes. Alright, so we finished part A, part B. Let's move to part C. So using curved arrows to show the movement of electrons, right, the mechanism for the conversion of A to B. So for the conversion of the alkene to the haloalkane. So let's do that part. Right, I'm just going to do the part of the double one and Alright, so here we have the alkene and the HBr. So what first let's look at the bromine molecule. It is what? I'm looking for a term. The bromine molecule. I'm looking for a word start with P.
Polar.
Right.
Polar.
That is correct. So therefore the hydrogen should be slightly
Positive.
right, and the bromine is slightly negative. So we know that the pi electrons in the alkene molecule will do what kind of attack on the hydrogen atom? What kind of attack will take place?
The nucleophilic attack.
Right? So should I use a curved arrow or a fish hook?
The curved arrow.
Right? Because we are moving two electrons from the double bond to the hydrogen. And remember we said that a nucleophilic attack is a dative covalent bond that is being formed. So two electrons are being transferred to hydrogen. Now what must happen within the HBr molecule? Is it going to break?
Yes, sir.
And it will break out.
Heterolytically.
Right. So bromine gets the two electrons from the bond. Right. And so now the carbon to carbon bond is broken. Right. I'm not going to draw bucket structures out here. I'm just going to focus on the carbon to carbon double bond. Remember, the hydrogen goes to the carbon of the double bond with the more hydrogen. So let me just put it in blue to differentiate them. And this carbon is going to be what? It's going to be a carbocation, right? So in the first step, we have the formation of our carbocation. So a nucleophilic attack on the HBr molecule, right? By the pi electrons. So let me just put that. So we have two things occurring. We have nucleophilic attack on the HBr molecule by pi electrons in the carbon to carbon double bond. And the next thing we have occurring is formation of a carbocation. So it's a nucleophilic attack that leads to the formation of the carbocation. Alright, the CH2, CH3 can hold. And over here, goes CH, CH3. Alright. So after the nucleophilic attack on the HBr molecule, anybody remember what happens in step 2? So this is step 1 of a two-step mechanism. So what happens in step 2? Anybody remember? Oh, I'm leaving off the bromide ion.
So you're going to have the nucleophilic attack of the bromide ion and the carbocation.
Alright, so nucleophilic attack on the carbocation by the bromide ion. Alright, so let's just grab out the carbocation. Of the bromide ion. Right. And of course, you would just add back what was here in the on it. Alright, so step 1, nucleophilic attack on HBr to get the carbocation and the bromide ion. When you're doing the mechanism, don't leave out any arrow. So don't just show the nucleophilic attack and don't show the homolytic, the heterolytic bond breaking here, right? And don't forget to put the bromide ion here, or the positive charge on the carbon. And then here we have the nucleophilic attack on the carbocation by the bromide ion. And you show it. And you end up with the final structure. If you want here, you can actually put a lone pair on it, right? So you show that we are donating a pair of electrons to the positive carbon atom. And that's it. It's just 2 steps. Nucleophilic attack, and then nucleophilic attack by the pi electrons, and in step 2, nucleophilic attack on the carbocation. Alright, so let's look at the next question. we did the mechanism. And so that's part C. And so this is part C. So for part D, it says state the name and reagents for a laboratory test that can be used to distinguish between compound C and propan 1-alpha. Compound C, what was compound C again? Compound C was the alcohol. Alright, so let's just, compound C was an alcohol, right? What kind of alcohol was compound C? I'm going to check what. But compound C was an alcohol. Alright, let me draw back the structure of it. Was anybody writing? I can erase. I think I can erase. Right, so the alcohol, let me draw the structure. So the double bond was here, right? And when we add the bromic, when we add the H, Br, bond was broken, and the H was here, and the Br was on this carbon atom. And in nucleophilic substitution, the OH would have replaced the Br, and so would have ended up with the alcohol. So the question is, for Shante, what kind of alcohol is this? And before I answer what type, how many types of alcohol do we have? What are the three categories?
Primary, secondary, and tertiary.
Correct. And what is that one on the board?
It's a tertiary
How you know?
because it's attached to two other the carbon with the functional groups is attached to two other carbon.
Two other carbons? How many other carbons is it? 1, 2, 3. So it's tertiary. So tertiary alcohol because the carbon with the OH group is attached to 1, 2, 3 other carbons, right? Or you can say the carbon with the OH, it has no hydrogen, right? So once the carbon with the OH group has no hydrogen, it is a tertiary alcohol. So it's a tertiary alcohol because the carbon atom attached to the OH group has no hydrogen atoms attached to it. And that is why they are not oxidized, right? A hydrogen, if you notice with secondary and primary alcohols, the carbon with the OH, it will have a hydrogen attached. To the tertiary alcohol, it has no hydrogen attached to it. As you can see, 3 carbons, but I prefer to look out for hydrogens. So no hydrogens are there, it is a tertiary alcohol. Alright, so how can we differentiate? Back to the question now. So part D, state the name and reagents for a laboratory test. So what is the name of a laboratory test that we can use?
Oxidation.
Right, so oxidation of alcohol, and the reagent for that would be
Potassium permanganate or potassium
right.
dichromate.
So the name for oxidation, right, and the reagents we can use potassium permanganate and sulfuric acid because remember we acidified the sulfuric acid, or we can use K2Cr2O7. I can just put acidified potassium permanganate. Acidified AMNO4 or acidified K2Cr2O7. And that was the end of that question. But they could have followed up, right, and asked for the expected observations, right? So what would you expect to see if you do this test? If you use KMNO4, what would be the expected observation?
Purple to colorless.
For which one? Well, oh, I have
For KMNO4.
right. And if you use this one, if you use dichromate, what would be the color change?
Orange to green.
Correct. So which one would be oxidized? This or the propan 1-al?
The propan 1-al.
Right. And propan
The
1-al,
propan 1-al.
right. And let's say they had asked you to explain, right? So why would propan 1-al be oxidized and propan 3-al, remember propan 3-al, and this one not oxidized? So why would propan 1-al undergo oxidation?
Because the propan 1-al have 2 hydrogens attached to the carbon with the OH.
Right. And it's a primary alcohol as well, yeah? And this one, it will not be oxidized because
It's a tertiary alcohol and it has no hydrogens directly attached.
right. So on the next paper, they don't have to ask for reagent. They can give you the reagent or the test and ask you for observation and explanation. Alright? So the final, the next part of 2018, number 4 of the 2018 paper. Alright, so butene is an organic compound used in the manufacture of commercial solvents such as the alcohol 2-butanol. They are unstated the name of Just state the name of the discrete formula of 3 isomers of butene include a pair of geometric isomers. So we want 3 isomers of butene including a pair of geometric isomers. So we know butene is, so we're doing number 4A. So butene is C4H8, right? So we can simply draw, we could do one butene, right? So I'm just going to give some options. This has too much hydrogen. No. 1, 2, 3, 4. Right. So we could do one butene. What else could we do?
Sir, add another 8.
Add another? Oh, here. Thanks. Which other isomer could we have done? So this is one butene.
And the 2 butene.
That is correct. So we could also do 2 butene. One more. There's one more we could do as well. So we can move up the double bond, and if you cannot move it anywhere else, what should you do afterwards? So if you cannot move the double bond to get an isomer, what should you do after?
So remove one of the carbons so you can get a methyl group.
Exactly, remove one of the carbons at the end. So if we remove this carbon, right, we have 3 carbons remaining. So 1, 2, 3, and the double bond must be in the chain. So we have propene. Can I put the carbon that I removed, right? Can I put it here?
No, sir.
No, sir.
Tell me why.
Because it would still be part of the chain, so it's still butene.
Exactly. Right? It would still be part of the chain, so it would still be 1, 2, 3, 4, which is butene, counting from the end closest to the double bond, 1. It would be 1 butene. So you are correct. So whenever we remove a carbon atom, it must go on a carbon in the middle. So what is the name of this alkene?
Two methyl, 1 propene.
Right. 2 methyl. One propene, or we can say 2 methyl, 2, 1 ene. Alright, so it asks for 3 isomers, but 2 of them must be geometric isomers. So you will do any one of these isomers, right? So we haven't looked at the geometric isomers as yet. So for the one isomer, you could do 1 butene, 2 butene, or 2 methyl, 1 propene. So you could do any of these. Right? Now let's look at these geometric isomers now. Right? So that's actually isomers, one that is not geometric and two geometric ones. Alright? They could pick any one of these. However, based on this structure, you wanted to ask a question?
No, sir, I thought you were going to erase it.
Oh, alright. Actually was. Right. But looking at the structures, right? One of them, these are the three isomers, right? So we look at all the possible isomers of butene. Now, one of them must be able to give us a geometric isomer. So look at the three of them. Can any of them give us a geometric isomer?
One butene and two butene.
Bear in mind the criteria. What is the criteria?
Butene.
Why, yeah, two butene can work. Can one butene work as well?
Yes, sir.
Tell me why.
No.
Technically they pick it up. So with one butene, tell me what to pick up. Why you said no? Tell me why you said no for one butene.
I see two hydrogens over one side.
Right. So even though each carbon atom of the double bond has a group in common, your carbon atom should not have two of the same groups. Right? So the criteria is, just a second. So you must look at the carbon atom of the double bond, and they must have a group in common. So this has hydrogen in common, so that's good. However, this carbon has two of the same groups in common, so it cannot work. So when you're looking for cis-trans isomerism, the carbons of the double bond, each individual carbon should not have two of the same atom or two of the same group of atoms. So let's look at this and why it cannot work. So C, double bond C, right? That's the double bond. So H, 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 yeah. CH2, CH3. Alright? So let's say we're looking at this, right? I'm saying this is cis because the two hydrogens are on the same side. So let's call this cis for a moment. So trans now, let's bring this up, the CH2, CH3. And then the H is here. Look at this carbon atom. Is there anything different on this carbon between these two? No. So looking at this carbon, H is here, H is here. So there's nothing different between them. So when one of the carbon atom has the same group attached to it, it cannot give us cis or trans. Right? So this carbon atom, it has two hydrogens attached to it, it cannot give us cis or trans. Even if it doesn't have to be hydrogen, if it has two methyl groups attached to it cannot give us cis or trans. Once it has the same, two of the same groups attached to it cannot give us cis or trans. Alright? When we do B with 2 we are going to see the difference. So just write off this and make a note of it. So this carbon atom, they have two hydrogens attached to it. So we cannot get the cis-trans configuration. Alright, so this is if we try it with build 1E. So we don't have cis or trans. Alright. Everybody clear on that? I can erase the board. 3, 2, 1. Alright, I can erase. So again now for 2-butene, I draw the carbon atoms of the double bond, right? Set up the cis trans configuration. Right? We have 2 hydrogens and we have 2 methyl groups. So you notice now with 2-butene, the carbon atoms have a group in common. Now you could use the hydrogens or you could use the methyl groups. But notice, when you look at the carbon atom individually, they have 2 different groups attached. So each individual carbon atom has 2 different groups attached, a hydrogen and a methyl group. But the 2 of them now, when we are comparing them, each of them has a group in common. A methyl, both of them have a methyl group, both of them have a hydrogen. So you could use any of these 2, but they must have a group in common. But they must not have the same group attached. So this was the case of build 1E. It had 2 hydrogens attached to it, but it must have 2 different groups. Alright? So which configuration is this? Cis or trans?
Cis.
Right. So what would be the name of it? It would be called cis, but
Sorry, is it 2-butene?
that is correct. It is cis. So you name it just like how you would name the alkene, right? But just put cis in front of the name. So it says cis 2-butene or cis but 2E, whichever way you want to name it. So for the trans now, right? So as you can see, the hydrogens, from the perspective of the hydrogens, they are on opposite sides, and for the methyl groups, they are also on opposite sides. So this is the trans but 2E. Right? So trans opposite sides, cis same side. Right? So these would be the 2 isomers that are the geometric ones, and you could have drawn the 2-methyl to 1-ene or 1-butene or the 2-butene. Alright. And that was actually 6 marks, you know. Draw and state the name. So to just draw and make right. So 1 mark for each name and 1 mark for structure. So that was 6 marks. And then for part 2, so that was A4A1. For part 2, it says draw the displayed formula of 2-butanol. Alright, so it says draw the displayed formula for 2-butanol. So let's do that. Alright, so that's 2 marks. Leave it right. Then for part 3, so this is part 2. For part 3, it says state with one reason the type of isomerism that 2-butanol is expected to exhibit. So state with one reason the type of isomerism that this is expected to exhibit. So what type of isomerism can 2-butanol exhibit?
Optical isomerism.
It can exhibit optical permeate.
Optical.
Optical, why?
Because there's a
Which, alright, which carbon is chiral?
carbon.
Starting from this end, which one of them is? Which one? Carbon 1, 2, 3, or 4? 3 is something.
Third.
So the second one.
Right, the second one. So it has a hydrogen, it has a methyl group, it has a OH group, and it has a an ethyl group. So it's optical, and the reason the carbon atom with the OH group, the carbon atom with the OH group is a chiral center. Let's put attached to instead of with the carbon atom attached to the OH group is a chiral center. Now, is optical isomerism the only one it can show? Or of others?
Sir,
Go ahead, Joanna.
I was saying yes, it has other.
Tell me which one.
Second, the position.
Position, alright. So, positional isomer. What's your reason?
So the OH can move over to the first carbon and you get 1
Right.
butanol.
Yes. If the OH group,
Sir, now see the board. I'm not seeing nothing,
I
sir.
mean, hold on, let me check. Hold on, see the board?
Yes, sir.
Uh,
Yes, sir.
so I hear something wrong with your connection. But
Sir, I
so,
see now.
alright. Right, so positional, if the OH group is attached to carbon 1, if the OH group is attached to carbon atom number 1, then it is 1 butanol. Alright, I can just put the position of the OH group can be on a different carbon atom. Yes, so you could just say that it's positional because the position of the OH group, let me put that one. OH group can be attached to any of the carbon atoms. Example, carbon number 1 would make it 1-butanol. There is a mixed isomer as well, you know. There's a mixed isomerism that it can exhibit.
I can get chain out of it.
Right. So we can get optical, we can get positional, we can get chain isomerism, right? So the arrangement of the carbon skeletons can be different. But, well, I think they're just referring to just optical. But let us say I have 2-butanol. Let me see the question again. So I say stated, no, not that. Not that. State with one reason the type of isomerism that this, right, so it's this specific compound, which one would it exhibit? So don't change the structure anything. So like, if you get 1-butanol, it wouldn't be, if you get what I'm saying, moving this will give you a 1-butanol, and it wouldn't be an optical isomer if you get 1-butanol. So I think the way the question is phrased, 2-butanol as is, what kind of isomerism it would show. So the compound as is, it would show optical because it has a chiral center. You understand? So as in, we could change the structure to get 1-butanol, which would give us positional, or move the methyl group, this carbon, could put it in the middle to get 2-methyl, 2-propanol. But the way the question is phrased, it says state with one reason the type of isomerism that this is expected to exhibit. So it has a chiral center, so it is expected to show optical. Understand?
Yes, sir.
Yes, sir.
Yes, sir.
So we'll just go with optical. Right? But if it had asked us, however, to draw a positional isomer, or all the possible types of isomerism that we can get from this, then we'll go the positional and the chain, and even convert it to the ether as well. Right? But it just asks us what type of isomerism it would exhibit. So we'll get optical. Right? And yes, we covered everything for this. Right, so this is where we close for today. Remember, it's recorded, so I'm going to upload it and send you the link. Alright, so let me just click stop recording.